All right, thanks for the invitation, and it's my great pleasure to speak here. And today I'm going to talk a joint project with Danny Ruberman and Nikolai Sobolev. It's on monopole Lefschetz number. Okay, so let's start with some notation. So throughout this talk, Y will be a closed, oriented, smooth 3-manifold. And so we can apply the package of monopole floor homology as defined by Kramer-Mrozka to get different versions of monopole floor homology of Y. So we have HM2, HM from, HM bar. And today we will use one more version, which is HM red. So Francesco just gave a great lecture on this monopole floor homology. So many of you should know a lot about this, but we will still quickly review the definition and the structure of this. Okay, so now we, by the work of Kudluhan Lee Taubes, or alternatively calling Gugini Honda and Taubes, we know that these monopole floor homology are isomorphic to the corresponding version of Higa floor homology as defined by Oshra's double. So they are pretty computable. So you can give you a 3-manifold, you can compute its monopole floor homology using this Higa floor homology. So now let's move one step further. Suppose we have a map from Y to itself. So it's a self-diffeomorphism. So this map will, by the functionality of monopole floor homology, this map will induce a map on the monopole floor homology of Y. So today we will focus on the reduced version. So we get a map from HM red Y to itself. To itself. So the motivating question is the following. So how can we try to understand and this induced map and try to extract geometric information. So that's the motivation for this talk. So we will try to understand how this map behaves on monopole floor homology, and we will try to draw some interesting applications. Okay, so yeah. So from now on, we will focus on the simple case that Y is actually a rational homology sphere. From now on. So we'll assume Y is a rational homology sphere, i.e. we assume the first Betti number of Y equals 0. And let me quickly recall the structure of monopole floor homology of Y, and also to set up some notation. So recall. We'll start with the version HM2YS. So here S is a spin C structure. Y. One remark that is kind of important here. So we will always use rational coefficient instead of Zemo2 coefficient, because eventually we want to consider Lefschetz number. So it's better we prefer to have some rational number instead of just 0 or 1. Okay, so we'll be using rational coefficient. Okay, so this has some properties. The important properties are, okay, so first of all, it's a vector space. It's actually a graded vector space, and it carries two grading. The first one is the absolute grading. It's a Q grading, and the second one is the sigma 2 grading. So it has, this is a graded vector space with two grading actually. So, and second, we have a U action that preserve this sigma 2 grading but decrease the grading by 2. Okay. And the third one is that there is a split short exact sequence. So that goes from 0 to Q U U inverse quotient U times Q U to HM and the quotient we denote it by HM rad. So the picture is like, the schematic picture is something like this. So of the vector space, draw an arrow between two dots if there is a U action that relates these generators, and so there is a, this basically represent a infinite tail that goes up to positive infinity, and this is always a sub of HM2. And if you take the quotient, you get some finite dimensional vector space where the U action is nilpotent. Something like this. Okay. So we denote this part to HM to be HM rad. Okay. So the schematic picture is something like this. Okay. And the fourth point, since we have this Q grading, we can define some numerical invariant outside this vector space. We define the absolute grading of this bottom term to be negative 2h. So we define negative 2h ys to be the Q grading of bottom infinite tail. In other words, if you take the Q grading of this guy, you get negative 2h. So this h is called Freud-Schoff invariant. And it corresponds to the Higa floor correction term defined by Auger-Zablo. Right. And before stating the theorem, let me give some definition about link signature. So this is a pretty classical invariant. So suppose we have a link inside. Okay, it's a link, unoriented. We do not put any orientation on it. So now if we put orientation, denoted by O, then we get an oriented link. So for an oriented link, you can draw a cipher surface, right? So you can draw a oriented surface, cipher surface with the boundary. This boundary orientation coincide with specific orientation. So we get cipher surface. So from a cipher surface, you can get a cipher matrix. Which we denote by V. Okay. And now, from this cipher matrix, you can take V plus Vt. You can symmetrize it and take the signature of this symmetric. And it turns out to be an invariant of this oriented link. So define it to be this link with this orientation. So let's just the classical signature sigma L, and it actually depends on this orientation. You choose different orientation, you may get different answers. But one thing you can do is always to get an invariant of the unoriented link. One thing you can do is you just take the average over all possible orientations. So take average over all possible orientation. You get a link invariant, which we call to be the Murasugi signature. So that's the Murasugi signature. All right, now we are ready to state the result. Suppose we have a link inside S3 with determinant non-zero. Recall that the determinant is just you plug in -1 to Alexander polynomial. So the determinant, we have a non-zero determinant link, and we let Y be the, so we let Y be the double cover of S3 branched along L. So we can take the branch double cover for this link. We denote it by Y, or we'll also denote it by sigma L. And we let F from Y to itself to be the covering transformation. Then that one can compute the Lefschetz number of this covering transformation of the induced action on reduced monopole floor homology, and express it in terms of the signature and the Freushoff invariant. So here, the absolute value of L simply denotes the number of components. So if you get a knot, it's just 1/8. If you have two component link, it's 1/4, something like that. And so here we take the Freushoff invariant of the double branch cover over and sum it over all spin structures. So this gives a formula to compute the monopole Lefschetz number. So some remarks. The first remark is that actually this you can state the theorem in an equivalent way, that if you have an involution on a 3-net manifold with quotient S3, something like that. So you see there's some constraint on this diffeomorphism F. First of all, it should be a self-diffeomorphism of order 2, and secondly, the quotient should be just the 3 sphere. But actually, this is in progress. We're working on a more general version. So formula for any finite order diffeomorphism on any rational homogeneous three spheres. So if you have any finite ordered self-diffeomorphism on a rational homogeneous sphere, you can compute the Lefschetz, the monopole Lefschetz number, and for simplicity, that L is a knot. Let's assume L is a knot. Assume for simplicity, let's just assume the quotient is an integer homogeneous three sphere. Then the more general version that is the following. So it's 1/8 m equals 0 to m minus 1 signature m over n L minus the sum of all spin C structure as spin C that is preserved under this diffeomorphism. And we take the sum of the corresponding Forshoff invariant. And note that in this case there is an additional term which is n times y quotient f. So let me explain this. So this is the Tristan-Levin signature. So it's a generalized version of the classical knot signature. And this is the Forshoff invariant, but now the sum is taken over all spin C structure that is fixed by this diffeomorphism. And this lambda denotes the Kazan invariant of the quotient. So in particular, when the quotient is S3, this term just disappears. So there's no this term, and so n is the order of f. So that's the formula we are expecting, and well, modulo some technical issue like perturbation, orientation stuff. So we have a sketch of proof. Oh yeah, sorry. Yeah, y mod f. Yeah, 6. Y mod f. And L is the French locus. Okay, so that's the first remark. And the second remark, one can compare this result with excess links result. The following result by Jianfeng Lin. So, which states the following: half of the signature, one can obtain the knot signature by counting the number of flat SU2 connection on the knot complement. I should put quotation mark here because one need to do some perturbation on the curvature equation in order to get transversality and more out gauge. Oh, sorry, I forgot one very important. So we require that the flat connection such that the trace of the flat connection, the trace of the holonomy along meridian equals 0. So excess result essentially says that you can recover knot signature by counting this traceless flat connection, SO2 flat connection over the knot complement. And it's actually our result can be thought as a self-written version of this. Right. Before going to applications, let me just give one example calculation. Okay. So we let L be the 2, -3, -7 press or not. It's just some specific knot, and then the corresponding sigma L is just sigma 2, 3, 7, and it can be written as a subset of C3 that defined by these two equations, Z1 squared plus Z2 cubed plus Z3 7. And Z1 norm square plus Z2 norm square plus Z3 norm square equals 1. Okay, so that's the 2, 3, 7 Briscoe sphere. And the covering transformation is easy to describe. It simply sends Z1, Z2, Z3 to the conjugate. It's defined by this conjugation. Now, so the Froishoff invariant of this Y for the unique spin structure is just 0. Okay. And the signature of L is just 8. And the monopole for homology of this Y, which I'm red, is just dimension 1, and it's supported in degree in gradient -1. So it's one-dimensional vector space in odd dimension. Okay, now so we can apply our formula to get the Lefschetz number of equals 2/16 times 8 minus 0, so it's just the 1. And since this vector space is odd graded, recall that the Lefschetz number is defined to be the trace of the even part minus the trace of the odd part. So we see that the trace of this F star should actually be -1. So as a consequence, that implies F star acts as if identity. So this conjugation action actually acts as negative identity instead of positive identity. All right, so that's the statement of the theorem. And instead of talking about the proof, let me spend the rest of the time talking about the applications of this result. So basically, this result gives us some first step towards understanding this induced action F star. And as I said, one can use this information to extract some geometric conclusion. So let me talk about some applications. So the first application is actually in four-dimensional gauge theory, and which is actually the actual motivating question for this project. So the first application. So we consider four manifold. let's satisfy the following two properties. The first one is that the homology of X should be the same with Z coefficient, should be the same as the homology of S1 cross S3. Okay, and the second is the homology of this X tilde. X tilde is just the Z covering space of X. This is the same as the homology of S3. So as you can see, so it's just something with the same homology as S1 cross S3. Okay, so we consider this kind of smooth form manifold. You will see a large family of such manifolds soon. And okay, so for such manifold, there are two gauge theoretic invariants that are available to us. The first one is denoted by lambda FO X. So it's defined as a quarter count of the number of anti-self-dual ASD SU2 connection on X and more gauge. And this is defined by Fruta Alta. It's a quarter of the Donaldson invariant for the trivial bundle. And the second one is lambda SW. Okay, so we see this manifold do not have a second homology. So the second Betti number is 0. So if you just count the number of Selbach-Witten solutions, you won't get a smooth invariant. It actually depends on the metric and perturbation. But one can remedy this by adding a index theoretic correction term. Such that this linear combination actually does not depend on the metric and perturbation. And this is defined by Morovka, Ruberman, and Sutliff. Okay, so these are the two gauge theoretic invariant that potentially can help us to obtain some exotic smooth structure on such manifolds. And sure, there's a conjectural relation between them. So conjecture. It's also due to Morovka, Ruberman, Sutliff. So conjecture says that for any x, one has lambda SWX equals negative lambda FOX. So these two invariants actually are equal up to a minus sign. So one can think this conjecture as a variation of Witten's conjecture in the case of vanishing B2, because the left-hand side is the Selbach-Witten type invariant and the right-hand side is the Donaldson type invariant. So this is actually a really interesting conjecture, and actually the start point of our project is to consider this conjecture in the following special case. We can as this mapping torus. So you take a knot inside S3, you take its double branch cover, and you form the mapping torus, i.e. you cross it with I, 0, 1 interval, and you glue the two boundary component not using the identity map, but using the covering transformation. So it's x0 is the same as fx1. Okay, so it's the mapping torus of the covering transformation. Let me xk. One can show that it always satisfies those two assumptions. So it makes sense to talk about these two invariants. And as a corollary of this Lefschetz number formula and some earlier work of us that express this lambda SW in terms of some floor theoretic number, so we are able to prove the following result. That this conjecture holds for this specific mapping torus. And actually they just equals, they both equals the 1/8 signature of K. Also, if our expectation for the general formula is right, the general formula for the Lefschetz number on a rational homology sphere, then that should imply this conjecture holds for any mapping torus of any finite diffeomorphism on rational homology spheres. K is a knot. Any knot, yeah. Any K. And so a more general version of this result will be this conjecture holds for any finite order mapping torus. Okay, so that's actually our initial motivation. Okay, so that's the first application. It's something from gauge theory, and let's do something more topological. Minus sign just, the orientation of the moduli space. They define, they deal with it in somehow different ways. So, it's kind of, very tricky to manage the plus minus sign. All right, and the second application comes from some four-dimensional smooth topology. So let's recall some definition. So let W be a contractible four manifold, or it's just a homotopy four ball. It's a D4. It's a four manifold with boundary homotopy equivalent to W to D4. Well, there are a lot of such manifolds, and be a diffeomorphism on its boundary. Okay, so we have a contractible four manifold with a diffeomorphism on its boundary, and there is, by the theorem of Friedmann, one can always extend this diffeomorphism as a homeomorphism of the whole four manifold. So tau always extends a homeomorphism on W. Okay? And the natural question is that does tau always extends as a diffeomorphism? And the answer, not so surprising today, but it was very surprising like 20 years ago. So the answer is no. And the first example was discovered by Archblut. So Archblut. Tau may not extend as diffeomorphism. And if so, for such W and tau, that tau cannot be extended, can be extended as homeomorphism but not diffeomorphism. We call this to be an Archblut cork. Are called and this subject is very important in four-dimensional topology because there is an operation called cork twist, which is the following. You can cut a four-manifold open into two pieces such that one piece is an Archblut cork, and you can regroup not using the identity map but using this exotic diffeomorphism on the boundary, and one can obtain a exotic smooth structure of four manifold by such cork twist operation. Actually, one can obtain any two smooth structures are related by such cork twist operation. So this is something very useful, and building on Archblut's result, we prove the following theorem. There is a, basically, let's say there is an absolute version of Archblut cork. So let me state the result. So there exists a integer homology 3-sphere Y such that the following, there exists the integer homology 3-sphere Y and an involution tau from Y to itself such that the following two properties holds. First one, Y bounds contractible for manifolds. So potentially Y can be the boundary of some Archblut cork. And the second one, tau does not extend as diffeomorphism on any homology ball bounded by Y. On any homology ball. In other words, no matter what you put in the interior of the homology ball, this tau involution does not extend as diffeomorphism. So actually, let me draw the surgery diagram for Y. It's actually just it's the following. One, two, three, four. Okay, so this is a two-component link. Let me make sure This is a two-component link, and one can do zero surgery on this link, and you can see from picture that there is a symmetry. One can rotate this link 180 degrees. There is a symmetry here, so that gives the involution. And actually, this is actually the boundary of the first Archibald clock discovered by Archibald. So what our theorem essentially says that is the interior of this Archibald clock doesn't really matter. You can put anything. As long as it's a homology four ball, this involution will not extend. So basically, we use that Lefschetz number formula to compute the action on this, the action of this involution on monopole floor homology, and shows that it cannot, and use that to show that it doesn't extend. Okay, so that's the second one. So when did I start? Okay, so I have 10 minutes more. Oh, about 20. Okay, good. All right. So that's the second application, and third one is about knot theory. So we use it to study the concordance of a concordance group. Okay, so the third. So let's say we have a knot inside S3. It's a knot, and we can define a knot in Lk to be just the Lefschetz number of the covering transformation induce the map on monopole floor reduce the monopole floor homology of branch double cover. Okay, so it's a number, it's a rational number. This is the covering transformation. The covering transformation. Well, of course, it's obvious that this is a well-defined knot invariant, and our main theorem essentially tells that one can express this Lk in terms of signature of K over 8 minus the Freud-Schoff invariant of the double branch cover with respect to a unique spin structure. So, but notice that both the signature and the Freud-Schoff invariant are concordance invariant. So we see that actually this linear combination is actually, this Lk is actually a concordance invariant. So this is kind of mysterious, at least for me, because this proof is quite indirect, and I don't see why such number should be invariant under concordance. So is that Lk is an additive concordance invariant. It's additive because both sigma and h are additive. Okay, so if you take the connected sum of two knots, the corresponding invariant just adds together. And the second corollary is that well, note that when K is coordinate of thing, when K has the coordinate of homology of K is as simple as possible, the branch double cover is an L space. So in that case, Lk just vanishes by definition, right? Because HM just equals 0. So as a result, that means Lk equals 0 for coordinate of thing knots, and as a corollary, one gets a relation between the signature and its Freud-Schoff invariant. So signature K over 8 equals H sigma K S for one of sin naught. And this relation was actually conjectured by Manolescu Ovens. They prove this conjecture for a special case of alternating knot, and Liska-Ovens generalized it to quasi-alternating knot. And now we are able to prove the full version of this conjecture. So for any quantum of sin knots, there is this relation, signature of the knot equal over 8 equals the Freud-Schoch invariant for the spin structure. And the third corollary is, well, now let's play the game that people have been playing for many times. So we have an additive concordance invariant that vanishes on all quantum of sin knots, so as a corollary. So if you take the smooth concordance so CS denotes the smooth concordance group, and you quotient out by the subgroup that is generated by all quantum of sin knots. And this contains a Z summand. So it actually contains it's actually Z direct sum something else. Okay, so that's the third application, and the fourth one is somehow something in contact geometry. So let's start. So let YC be a contact 3 manifold. Then Kroheimer-Morovka actually defined a contact invariant in monopole floor homology. Gives that is some element in the monopole floor homology. Let's use this 2 version, HM negative Y, the 2 coefficient. So it's some element in the monopole floor homology of the orientation reversal with Z 2 coefficient, and they also define the version coefficient. Let me use this V tilde. So let Z coefficient, but not quite up to plus minus sign. So there is an ambiguity of this plus minus sign in the Z version. Technically, that's because in order to define this contact invariant, one need to attach a contact cone on the 4 manifold. One need to attach a contact cone and consider the Stolper-Witten equation on that 4 manifold. But the Stolper-Witten moduli space, it is orientable, but there's not an obvious canonical orientation on that Stolper-Witten moduli space. So if one try to count the monopoles, there is an ambiguity of plus minus sign. Well, so this seems like some kind of very technical reason. But so one might hope that maybe one can get rid of this sign ambiguity by some further analysis. The answer is quite kind of disappointing. So the question is, can we get rid of this plus minus ambiguity in the the definition of this contact invariant? The answer, kind of disappointing, is that there is note that this contact invariant has a counterpart in Higa-4 homology defined by Audra-Zabel and Honda, Kazes, and Matic. They proved in the context of Higa-4 homology, and also we prove in the context of monopole 4 homology that the answer is no. So you can never find a canonical sign assignment for this contact invariant. Our proofs are quite different. With theirs, so they use quite complicated machinery, suture TQFT, to prove this result. But our proof is that we are able, using that Lefschetz number formula, we are able to find some contact structure on some specific Briscoe sphere, such a certain involution that preserve the contact structure but actually change the sign of the contact invariant by -1. So as a corollary, there is no canonical sign assignment in this contact invariant. All right, so let's see, still have like 5 minutes. Okay, so let me talk a little bit about the proof. How do we prove this Lefschetz number formula? Well, so the original version, the version I wrote down here, is the proof used the scan triangle. So if we have a knot, we have a link with a certain crossing, we can resolve it in 2 ways. So you have 0 resolution, 1 resolution, and if you take over these three manifolds are related to each other by surgery, so there is a surgery Z triangle that relates this monopole 4 homology. I'm not sure about the direction, but there is something like this. And moreover, there is a covering transformation on each of these three manifolds. So one can define the map in a compatible way, such that there is an overall ZMO2 action on this whole Z triangle. So if you have a ZMO2 action on this whole Z triangle, you expect some kind of total Lefschetz number equals 0, some conclusion like that. As a result, one obtains some certain skin relation for this Lefschetz number, and using that skin relation, you can essentially reduce the problem to the unknot. So that's the very schematic proof. There are certain technical difficulty in that. For example, one need to do certain truncation, and if one do truncation, then there are some constant involved, and one need to show that those additional constant vanishes, something like that. But this proof doesn't quite generalize to a more general version. If you have any knot in a 3 manifold, you take its nth branch tuple cover, you take its nth branch cover. How do you do resolution? I don't know. So this proof doesn't quite generalize to the more general version we are working on. And the more general version uses a quite different technique. So basically, by the work of Baldrige, we are able to reduce this monopole Lefschetz number count to the problem of counting Zelber-Witten invariant on certain three orbifolds. You just treat the quotient y by f is, you can treat it as an orbifold with certain singularity. So one need to count the Selbel-Witten invariant on these 3 orbitals and relate it to the knot signature. So that's the that's the current version that we are working on. Okay, so I think that's all I want to talk.